All right, good morning, Al. Thanks for joining into this webinar. It's my pleasure to announce a couple of colleagues of mine from Argonne Lab on my SIDAC project who have been doing some really nice work in some workflow management tools and in situ data transfer, mostly for us targeted at Lagrangian particles at scale. So Tom Peterko has been at Argonne for a little about 10 years or so. I can't remember exactly, and I don't
18,
have the
18.
18.
18. It was
Yeah,
2007. Sorry,
yeah.
I had that in my head. And Orcun is a newer addition to Argonne, and
Eight.
so I
How,
Eight.
8 years for
ate
Orchard.
in 2017.
Yeah.
See, I had him exactly flipped. Well, I will turn it over to them for the presentation. Thank you.
Okay, thanks for the intro and thanks for inviting us and welcome. I'm not going to spend a lot of time on this title slide, but hopefully in the first couple of slides, we'll understand what we mean by high performance workflows, in situ data transport, and workflow management. So I'm going to just jump right into it. So, we're familiar with your E3SM coupled, climate system, and the driving problem here is how do we attach additional codes, be they analysis, visualization, MI, ML, to the outside of what you already have in your workflow. So, and also, how do we develop and build these codes separately so that they're not function calls or subroutine calls inside E3SM, but they're totally separate executables in different languages, having their own set of dependencies, build systems, whatnot. For example, a tracker for atmospheric rivers in the atmosphere or water mass transport analysis code in the ocean, or Lagrangian particle tracing, as Luke mentioned, that we currently work on, but outside of the light module that is inside of MPass Ocean, but totally external to it, and maybe hooked to that a classifier that looks at finite time Leopoldov exponents, just as an example. And even though these are being built separately, how do we connect them all together into the same job launch so that they run in a single HPC job? And how do we have them communicate effectively with each other and with the simulation codes through the interconnect, preferably through MPI rather than through the file system? So that's what we're trying to solve. And we'll talk about the software infrastructure, the middleware that we've developed to do that. So that's what this talk is about. First, one or two definitions. We call this a workflow, and a workflow is a set of computing tasks that coordinate to do something, in common. And in situ HPC workflow is a workflow that runs on an HPC system within a single job launch. That's what the in situ part means. And mentally, we can think of that workflow as this directed graph that you see where the vertices are the codes or the executables. We call them tasks, but these are full programs. And the edges are the data dependencies or the data transfer or the communication between them. And note too that this can have cycles. It's directed. It doesn't have to be acyclic, so there can be feedback as well. And in terms of software structure, we think of primarily two layers in the middle of this software stack. At the very bottom is MPI and IO libraries like NetCDF and so on. At the top are your codes. And in between them, the middleware is a data transport layer that we call Lo5. We'll spend a slide or two talking about that. And on top of that is a workflow management system that we call Wilkins. And we'll spend a few more slides talking about that. And then we'll wrap up with an application to E3SM and particle tracing in MPass Ocean. So that's the structure of the talk. So we'll start with the Lo5 data transport library. This is public. It's on GitHub. And just very briefly, the objective of Lo5 is to move data between codes between tasks in the workflow without having to modify the task codes, and to do this in parallel in a distributed memory way. And the way that that's implemented is that Lo5 is built on the HDF5 data model as an HDF5 vol plugin. Vol stands for Virtual Object Layer. This is a way to inject custom code behind the HDF5 API. And the custom code here is to basically bypass the storage system, package up messages, and send them from one code to another behind the scenes. So to the programmer, to the code, this looks like just plain old file I/O, but with the appropriate switches in the configuration file to switch from file mode to MPI mode, we can bypass the storage system and do this in a parallel way, redistributing data. And Lo5 is independent of the Wilkins workflow manager that sits on top of it, so other workflow systems can use it as well. And the way that this is implemented is in memory, in distributed memory on each MPI rank. There is this metadata tree that basically mimics the HDF5 file structure. So we have files and groups and data sets, and all of the entities that are available in the HDF5 data model are built up in a metadata tree in memory. And then as codes issue file I/O operations, we access this metadata tree in memory, grab the data, package it, send it from one code to the other rather than to the file system. So that's the basic idea. And in practice, the performance advantages are what you would expect. The green line is we can do this in memory mode or file mode. We can still go to the storage system if we choose. But of course, the memory mode, which is the MPI sending of messages through the interconnect, is much faster. This is the green line. Lower is faster here. This is a weak scaling test up to 16,000 MPI ranks. So that's to be expected. And with that, I'm going to now change gears and move one level higher in the software stack to talk about the Wilkins workflow management system. And for this, I'll turn it over to Orcun, who will describe that part of the software.
Thanks, Tom. Wilkins is an in-situ HPC workflow management system that is built on top of the Lo5 library that Tom just presented. And when developing Wilkins, one of our main design objectives was usability. And in Wilkins, we have an easy-to-use workflow definition interface to describe the scientific workflow graphs. Also, we don't require any modification to test codes if they already use HDF5 on any of the front ends to HDF5, such as NetCDF, Scorpio, or H5Py. And also, given the diversity of scientific workflows we have today, we wanted to support various task graph topologies, ranging from simple linear workflows to more complex workflows, such as ensembles and cycles. And in Wilkins, we also support both stateful and stateless tasks. In the next slides, I will be focusing on the workflow definition interface of Wilkins to show how we can describe data-centric workflows and ensembles. In Wilkins, we provide an API for users to define the workflow graph. And here, what users do, they indicate the data and resource requirements of the tasks. Let's say, for example, we have a workflow graph like the one you see on the left, which consists of 3 different tasks. One producer coupled to 2 different consumers. Here, producer generates 2 data sets that are grid and particles, while consumer 1 reads the grid and consumer 2 consumes the particles dataset. And on the right side, we have the YAML file when we use to define this workflow graph. And here, we basically use outbound and inbound fields when the user defines data requirements. For example, for producer, we say we generate this grid and particle datasets, and similarly, we define the incoming data from the consumer tasks. Then, based on these data requirements, Wilkins automatically creates the communication channels between these tasks, which is entirely transparent to the user. Hence, we will have one communication channel for producer to consumer 1 from the grid dataset, and another one between producer to consumer 2 from the particles dataset. And if you look at this file, also we can see how we exercise some of the lo-fi properties. As Tom mentioned, from the communication method, we can easily switch between file and memory. And here you see that memory is set to 1, which means that these tasks are communicating over an MPI between each other, but we can easily flip this by setting file to 1 and memory to 0, and at that point we will be communicating over files instead. And also we use this file to indicate what are the resource requirements from these tasks. And if you see at the top, we have the nprox field, which means that producer is going to have 3 processes, consumer 1 has 5, and so on. And then based on these resource requirements, Wilkins will assign this resource to this task and then launch them as a single HPC job. And here we have some results from the experiments that is measuring the overhead of Wilkins as a workflow system compared with using Lo5 as a standalone library. And we use here 3 different data sizes and up to 1,000 ranks. And on the y-axis of this figure, we have the completion time. And if you look at the figure, we see that all the times are similar for any of the configuration. That says us that the overhead of Wilkins on top of Lo5 is really negligible. As I mentioned, we also support large-scale ensemble workflows with Wilkins, and here main question is how can we define these ensembles in a workflow configuration file? As often we have too many tasks in an ensemble, we cannot really expect users to indicate all of these tasks in the config file, which will be really burdensome. And instead, what we do in Wilkins, we have an optional task count field. And when we use this field to indicate how many instances in an ensemble. And with this little extra information, we can compose ensemble topologies like the ones we see on the left, such as fan out, fan in, end-to-end on any combination of those. And again, like we saw in the data-centric workflow definition, Wilkins will create the communication channels between these ensembles without users need to explicitly define them in the config file. And we have some sample of it on the right, when we have a fan-in topology of such a workflow with 4 producers and 2 consumers, and only change that we have to do to indicate such ensembles to indicate this task count field with saying that we have 4 producer tasks and 2 consumer tasks, and that is the only information needed extra to define such ensemble topology. And again, here we have a performance study from a molecular dynamics simulation, which was a nucleation event that we freeze the water, that is stochastic, and variant event that requires launching multiple ensemble instances of molecular dynamics simulation. And in this experiment, what we did, we ran up to 64 lamps molecular dynamics simulation coupled to the analysis task, which was a feature detector that analyzes the crystal structures of this ice forming. And then on the figure, we see the completion time on the y-axis again, and this was a weak scaling plot. And if you look at on the x-axis with respect to number of ensemble instances, we see that this time is almost flat, which shows that we can support effective execution of ensemble workflows with Wilkins without adding any significant overhead. And now I will give back the floor to Tom to talk about application of our software to E3S.
Thanks, Orcun. Within Luke's impacts project, the test case that we've been playing with so far is the SOMA test case. The workflow on the lower right, well, upper right is a diagram from Phil Wolfram. You probably have seen this, just a kind of cartoon of the double gyre SOMA behavior. In the lower right, we see MPass Ocean coupled to FTK, that is our particle tracer, again, external to MPass Ocean. It runs on GPUs, it's written in C++, totally different code than MPass-O. coupled through low-5s and communicating by MPI between MPAS-O and FTK. Optionally, we can also write checkpoints to storage from MPAS-O through file IO. The path lines that are traced by FTK are written out to storage and then subsequently offline read into ParaView and visualized. And we'll show you some examples of that in the next couple of slides. So we ran in this test, we ran MPAS Ocean, we ran the SOMA test case of MPAS Ocean at 32 kilometers resolution, and we tried various simulation times, 6 months, 1 year, 2 years, and 4 years. The data transfer was done through memory, through MPI. The whole thing for the 1 year run took about 2 hours to execute in total. And the pathline particle tracing was 2,500 path lines on a grid of 50 by 50 seeds. You can see a view of that in the lower right. You can see the double gyre effect, similar as in the Wolfram paper, clearly from the path lines. You can see the mixing in the middle, and if you zoom in, this is just an example of the rendering that we're doing in ParaView. We're using tubes that include lighting and glyphs to show the velocity direction. Colors are velocity magnitude. And the thing that we're interested in here is what is the right frequency of outputs to generate these path lines? How frequently should we generate output? How long should we run for? Where should we place the seeds to start the path lines? How many seeds should we place? Things like that. So going forward, we'll be scaling this up, and we'll be doing some more accurate performance profiling that we haven't done yet. And so, in summary, first of all, let's just look at the software stack. These are 3 different applications, but the far left one is the one that is of interest to this community. So we have Wilkins, we're running E3SM. E3SM is doing its outputs through the Scorpio IO library, which is using NetCDF4, which fortunately is compatible with HDF5. So it's at that point that Low5 can grab the data and redirect it, and then use MPI to route it from between tasks. The other 2 columns here are just different applications. The middle one in cosmology, the far right one is an AI application, just to show that this is agnostic. This is not built only for climate. This is an agnostic system that is general purpose. And so what we talked about are 2 layers of software. Low5, the data transport library built as a Vol plugin that allows us to bypass and send data over MPI instead of going through storage. And does that fairly seamlessly as long as the codes are compatible with HDF5. And then on top of that was the workflow management system, Wilkins, that uses Low5 to do its data transport, has a data-centric workflow definition. Orcun showed you the configuration file for that. Another feature is the ability to easily multiply tasks into an ensemble of them. We haven't talked about other features like flow control or custom actions that are outside the scope of this talk. Going forward, we are now moving from using this system to build MPAS-O as a standalone code to building the entire E3SM software stack. We're well on our way to doing that. We're adding additional analysis codes to the workflow, not just particle tracing, but for example, one of our collaborators in the Impacts project has a Python water mass transport code that we'll be plugging into the workflow. We'll be continuing to do profiling and benchmarking and helping teams eventually to use this for production. So with that, I guess we finished with more than enough time for questions, and we'll be happy to take those. I'll stop sharing, and we're happy to hear your thoughts and answer any questions that you may have.
Thank you. Great talk.